In previous videos, we saw that an electromagnetic wave is made up of a time-varying electric field and a crossed time-varying magnetic field. Crossed meaning they're mutually perpendicular to each other and mutually perpendicular to the direction of propagation. In this video, we're going to look at the relationship between the E field and the B field. What I said before was that they are in phase, which means that basically when the E field peaks, the B field peaks. When the E field is zero, the B field is zero, and so on and so forth. Now, there's a really simple equation which describes the relationship of the E field and the B field, and it's this. At any time, B is equal to E over C, where C is the speed of light, the speed of the electromagnetic wave. So notice this works really well when B is at a max. It's equal to E max over C. When B is equal to 0, the only way this can equal 0 is for E to also equal 0, which tells you that they're in phase. For when B is a minimum, E is also a minimum. So this equation is useful. What we generally do is look at the maximum value of the B field and the maximum value of the E field, which, as I've said, occur at the same time. Now, if that's the case, if we just agree to call the maximum value of the B field some B naught, that means that this is equal to the maximum value of the E field, which we'll call E naught over C. So both of these equations are true. This one turns out to be the one we're going to use more than anything else. But this is also true. But of course, if this is true, this is true, because this is just picking off one particular point in time where the B field and the E field are both maximized. Now, that's a really simple expression that relates those. As it turns out, we have another way to characterize electromagnetic waves, and that is with the intensity. The intensity of a wave, the best way I think to explain this is by giving you some examples. The intensity of a sound wave would be the volume. The intensity of a visible wave of light would be the brightness of it. The intensity of water waves would be the height of them. So intensity, I think it's an intuitive thing to understand. But because we have two different changing fields here, we have a wave component made up of a changing B field and a changing E field, you have to ask yourself, okay, well, if I'm looking for the intensity, doesn't that change, first of all, because B and E are both changing in time, and the answer is yes. And then the other one is, well, which one do I look at? Do I look at the B field to determine the intensity? Do I look at the E field to determine the intensity? So the answer to the first question, does it change, is yes. So because of that, looking at the intensity at any given point in time turns out to be not very useful, because that is always changing. The easiest thing to do and the most useful is to look at the average intensity. We want what we'll call I average. Now the second question, how do I determine this? Do I look at the B field or do I look at the E field? The answer is you can look at either one. So I'm going to give you two forms of this equation, one in terms of the max E field and one in terms of the max B field. Here's the average intensity in terms of the max B field. Sorry, max E field. We've got the speed of light times the electric permittivity times the max value of the E field squared over 2. You can imagine that the over 2 has something to do with the averaging process. But notice what we have here. We've got the electric field, it's squared. This is the max electric field. We've got the electric constant, and we've got the speed of light. All makes a lot of sense if you think about it. Now, we have another one, I average, in terms of the B field, which is this. Speed of light again, maximum B field squared over 2 mu naught. So I still have a 1/2 here. I still have the speed of light. I've got the B field, the max B field, but now I have the magnetic permeability. I'm going to make that look a little bit more like a mu. Magnetic permeability, notice this appears in the denominator, whereas the electric field appears in the electric constant appears in the numerator. That's okay. Remember, there was the same situation when we saw the equations for fields. You know, this is in the denominator in the electric field equation. This is in the numerator, the magnetic field equation, so that might not be that surprising. But either one of these equations work. So if you're asked to determine the average intensity of an electromagnetic wave, and you're given only one of the Emax or Bmax values, you pick out of this equation whichever one you have, and go with it, right? If you're given the B field, you pick out this equation. If you're given the max E field, you pick out this equation. Of course, you could always do either one if you know how those max values are related, which is right here, right? So electromagnetic waves, as far as what we do with them, are not that complicated. They're complicated to think about, and there's definitely some complication to them, but the way we use them in this course really doesn't go much past this. Now, of course, you could be given an average intensity and asked to solve for the max E field in terms of that, and then asked to find the max B field in terms of that. But with these three equations, you really can handle anything that I am going to throw at you.